So in this video we're going to talk about mass storage, hard drives. Mass storage is an older term for where programs and data are stored when the power to the system is off. These days that can be a magnetic hard drive, flash card, SSD drive. It's also good for long-term storage of file, video, music storage, bigger files. And the word hard comes from the fact that it doesn't go away when the power is removed. We don't have anything called soft storage, but soft storage is something that goes away when power is removed. A computer is always trying to get its data and instructions from RAM. That's normally where everything lives, but when something is not used very often, it gets unloaded from RAM and put into the hard disk. And actually, to the computer, the hard disk doesn't look like a filing cabinet or a storage thing. It really just looks like more memory. It's just slower memory because it's off on something like a hard drive or something. And as data is needed by the CPU, it comes out of the hard drive or from those other memory locations and copied into main memory. And if you remember, I don't have it here, but when we talked about CPUs, there's even more RAM in the CPU that is fed by system memory. Now, types of drives, what we call a magnetic hard drive, because it uses magnetic platters to store the ones and zeros. Flash memory, SSD cards, USB flash drive, SSD solid state drive. This is all non-volatile memory, meaning it doesn't go away when the power is removed. Optical drives and tape drives. So an optical drive is a DVD or Blu-ray or CD-ROM. You can, with an erasable, you can write to it, certainly. And a tape drive is still used in some large-scale backup situations for long-term storage. It's really just a reel of magnetic tape or a cartridge of some kind. It's not very fast, but historically it's had a very high capacity. It's still called it, but it falls into the category of mass storage. All right, let's first look at the magnetic hard drive. And the magnetic hard drive, it's called a hard disk drive, HDD. It's composed of individual disks or platters. And these are very thin, made out of something, and coated with usually often aluminum, and often coated with a magnetic coating. This is a drive that has two platters. There are actually four heads there, one for each side. I know there's not much room there, but it'll fit in between there. There's actually a top and the bottom of this one, top of that one, that will fit in there. Those heads that are here go back and forth across that platter, reading ones and zeros or reading the magnetic fields. Now this is the inside of the drive. Normally all this business here is sealed inside a metal case. So once they manufacture it, this is sealed off, and you would never open it for normal servicing. Now, the closer those read-write heads are to the platter, the more densely the data can be packed onto the drive, which means that those heads are really, really close to the platter. There is a little bit of an opening in there with a filter designed to equalize that air pressure, and these platters spin anywhere from 3,500 to 10,000. Actually, standard speeds are probably 5,400 RPMs, revolutions per minute. So they're spinning continuously. Normally, if it's in operation, these are going to be spinning continuously, and those heads are going back and forth. The higher speed drives use a little bit more power, generate a little bit more heat, but they have faster data input and output because the disks are spinning faster. Now, here's kind of a picture. The data is actually stored on the drive in terms of a ring, but there are a series of tiny magnetic fields called fluxes, and they can be programmed to either be here's one that's this particular south-north polarity, or they can be flipped to be north-south. And so that's a process called flux reversal, and fluxes in the south to north orientation would represent a zero, a digital binary zero, a bit, and a flux in the north, that's the diagram's a little off there, flux in the north to south would be a 1. It's not really, you don't ever get down to that level normally, but as that drive is spinning, those heads are either sensing the direction of the magnetic field or applying a small signal to actually flip the direction of the magnetic field. And heads are an important part of a hard disk drive. And for every platter, and some disks have 4 platters, some disks have 2. I'm not sure what the maximum is these days. And each platter has 2 heads. Now, sometimes hard drives have an extra head or 2. Maybe a platter is designed as a backup and a head is designed as a backup. Now, one thing about these drives is that head is supposed to float on top. Now, one of the problems with hard drives is they're very mechanical. This is spinning, this head is going back and forth. If you suddenly move a hard drive, drop it or throw it in the air or whatever the case may be, the heads are very light, but they do have a little bit of inertia. And you can cause the heads to actually dig into this platter, and it will cause damage to that magnetic coating on that platter, and you lose data. That's why today's hard drives, especially in laptops anyway, have a accelerometer designed to sense when there's a sudden g-force, and they will actually park or shift the head over very quickly over to an area on the platter that is sort of sacrificial, can be damaged. Sometimes you hear this word called parking the heads. Parking the heads means putting the heads over to one side. I actually don't know whether it's on the outside or the inside, but to a place where if something happens, that the head hits the platter, it's in a space where there's no data stored. Now, those fluxes, those little magnetic fields, are stored in concentric circles on the platters called tracks. So this is a track, and this track here, depending on the density of the hard drive, it may be thousands and thousands and thousands of bits in one track. And there's many tracks across here. I don't know what the width is, but it's very small. So they pack a lot of tracks on these platters. Now there's a word sometimes you'll see, especially with older drives, called cylinders. And what a cylinder is, it's a group of tracks that occupy the same same position on the platter, on multiple platters. They're the tracks with the same diameter. That's called a cylinder. In the olden days, when you dealt with hard drives, you often had to specify the number of tracks, the number of cylinders, number of platters, very specific. These days, these drives have gotten a lot smarter, or certainly been smarter for the last 20 years or so, that they have electronics in them that keep track of the cylinders and tracks and all this business. And the computer just really is just sending data to and from the hard drive, and the hard drive is taking care of putting it where it needs to go. Now we've increasingly been moving to a solid state drive. And a solid state means it uses physics, semiconductor, silicon, to store the ones and zeros instead of a magnetic field. So there's no moving parts, there's no heads, there's no spinning disks. It's quite a bit faster. If you look at this disk here, this is spinning. Let's actually go to this picture. This disk is spinning, the head is going back and forth. So if the hard drive wants to access a very specific bit, It first has to position the head onto one of the tracks, and that does take a little bit of time to shift that head back and forth. It's pretty quick, but it takes a little bit of time. And then also the disc, even though it's spinning at maybe 5,400 revolutions per minute, it does take a little bit of time to actually, if this is the sector we're looking for, and the head is over here, that actually has to spin all the way over there to get to that head. Now with an SSD, it's really there's a little bit of matrix business going on inside that memory, but it's quite a bit faster. There's no waiting for the head to go back and forth, and no waiting for the drive to spin. Now, while they are faster, they are a little bit more expensive. We'll look at that in a minute. Now, they are what we call flash-based drives. There's different technologies for flash-based. There's a NAND-based, and there's a couple other ones. It's all kind of under this general category of solid-state drives. And this is in a package that looks like a hard drive package, a 2.5-inch hard drive. It comes in different form factors, but it's really the same memory that's on your mini SD card that's in your Raspberry, card that might be in your phone, card that might be in your camera. Now, flash-based solid-state drives are replacing or augmenting magnetic drives because they use less power, so they're very popular in mobile systems. And you'll find that lower-end laptops will often come with a cheap magnetic hard drive. Once you move up in price, you may see some laptops that have no magnetic hard drive and just an SSD. They cost more, but they use less power. Your battery lasts longer. Less heat. SSDs are faster in reads because, again, there's no spinning or moving the head. They're also pretty rugged. There's nothing to break. There's no head that digs into the platter. Disadvantages. They're higher priced, both often in overall price and just really dollars per gigabyte. Now, the capacity is less. Hard drives, 1 to 4 terabytes, you can find 6 terabyte drives. And SSDs, generally you can certainly find larger SSDs, but there's a sweet spot in the price. And the sweet spot tends to be around 512, although increasingly I'm seeing 1 terabyte SSDs around 2. So before we look at some specific drives, let's look at form factors. So magnetic hard drives are usually all connected to the motherboard with a cable, and they come in a 3.5-inch wide form factor for desktops, a 2.5-inch wide, a little smaller, not as deep, for mobile systems, and in general capacities are a little bit less than the 2.5. For a while before SSDs, before they really the flash memory industry really ramped up, you did find some 1.8-inch models. I think you wouldn't really find them anymore except as a possible replacement situation. Now, SSDs, solid states, come in a couple different forms. Of course, there's the flash card memory that you're familiar with on the Raspberry. But inside PCs, desktops, and mobiles, they're shaped, or they fit into a 2.5-inch form factor, just like the magnetic hard drive. Maybe not quite as thick. Also connect with a cable. Quite a few motherboards come with something called an M2 direct connector on the motherboard. It's a little tiny. These fit flush with the motherboard. There's a little tiny connector. These fingers go into that connector. It bypasses some of the Southbridge PCH functionality. It's often a more direct connection to the CPU. Certainly, if you have a choice, you're going to want to use the M2 SSD versus an external SSD. A little bit faster, and also just save space inside the case. And then other drives will often connect via some peripheral bus, often a USB bus. So you can have external hard drives, something like this in a case that's connected to a USB interface. So let's look at some practical drives that you can buy. And so here I am on Newegg, and I'm under storage devices, and kind of has the range. There's the magnetic hard drive, solid states, tape drives are often under here, CD optical drives, USB drives. Hard drive enclosures don't have drives, they're just basically cases to attach drives to a system with a USB. Let's look under hard drives, kind of walk through some of these different categories. Desktop, usually the 3.5 inch, 2.5 inch. These are all, usually external, means they come with a case. If you have a Mac, you need it's the same magnetic hard drive that's in a PC, but it's sold differently. All right, let's look at desktop internal. And let's kind of limit ourselves to 4 terabytes. That's a common size these days in desktops. Now, there's actually not very many manufacturers of hard drives. Really, you have Western Digital, Seagate, Toshiba, and then HGST is a subsidiary of Western Digital. HGST used to be a separate company, and actually, according to surveys, it was one of the most. It was a manufacturer of drives that were more reliable than any of the other ones. Anyway, and Dell and these other companies, they're just reselling Seagates or Western Digitals. So let's kind of limit ourselves to the top 2 or top 3 manufacturers. The HGST is still sold as a separate unit. Let's pick new. I'm just going to kind of try and limit the number of choices I have here. That brought me down to, I think, 100 or so. Inside there, let's see. Now let's also, just to make it consistent, I'm going to just pick a... You can see we go up to 8 terabytes. We can look at that in a minute. Those are going to be more expensive. I'm just going to stick with the 4 terabytes, which gives me 36. And I can kind of see, I've got... there's one on sale for 109, so that's a Seagate, 4 terabytes, 64 megabytes cache. This one has 256. Each of these drives has a little bit of system memory, RAM. If it supplants, I guess, the main memory. So if something's not in main memory, it's going to go to the hard drive. It's going to try and cache it in that little bit of memory. These add a little bit to the performance. The more cache you have, you get a little bit more performance. Not much though, but certainly more cache is always better than less cache. So anyway, let's see. We're down there around 114. Let's walk up to here and look at the high end. And you can see we go quite a bit. We're easily double the price. And what you get in this price range, some of this is supply and demand, but these are enterprise drives. And so these are enterprise drives. These are meant for data centers, systems where the drive is just continuously on. It's continuously going, unlike a common desktop PC where the drive spends a lot of its time just not doing anything, either powered off or not intensively being used. And these, the cheaper ones are consumer drives. Now let's pick, let's just stick with Seagate for a second here. Now you'll see sometimes there's also different surveillance drives. So a surveillance drive is something that's meant for a system that's continually acquiring video data. So the drive is always spinning. This drive, the Barracuda, sounds impressive, but the Barracuda may not be designed for something that's continuously on. Maybe they don't have quite as much heat dissipation. Some electronics may be cheaper. And also there's something in here. Let me see if I can do a compare and if it shows. Let's pick a... By the way, you see that's faster, 7,200 RPM. Down here it doesn't say, but it wouldn't surprise me if this is, or that's 5,900 RPM, a little bit slower. So let's take a cheaper one and do a compare. And on the surface, it looks the same. This is kind of confusing, but it has the same interface, SATA 6 gigabytes per second. The cheaper one is slower. More expensive one has more cache. More expensive one has a lot more, certainly, text to do it. One thing I can't see from here, and let me click on this real quick. It's also the warranty situation. Let's see. So this $100 was a $115 drive, okay, has a 2-year warranty. So after 2 years, if it fails, you don't get your money back. Although a drive failure is not good. All they do is just either refund your money, often send you a refurbished drive of the same capacity. They don't actually fix it. Now if I go down to here to one of these, let's see what the warranty is on one of these. So there we have a 5-year warranty. So some of that price difference is really to pay for the warranty cost. The difference between these two drives, I mean, fundamentally, many of the parts are the same. I don't think they're deliberately selling you a bad drive when you're paying less. Some of the parts are better, but a lot of what you pay is just, it's guaranteed to be more reliable. Whether it is more reliable is another case. Now here I've loaded up a web page from a company called Backblaze, and Backblaze is a cloud storage company. They're also, meaning they just store data for individuals and companies on the internet. And so they have data centers which are really filled with racks and racks of these magnetic hard drives. And they use a lot of them, and they save their statistics from the drives and track what fails and what lasts a long time. So you can kind of look at their data, and let's see, if you kind of, there's some outliers, but generally, actually the Seagate, well, these Seagates that's a terrible statistic for Seagate, but they don't have very many of them. So if you look at the Seagate, they have quite a few of those, 3.27%. Seagates used to be more reliable than Western Digitals. Now it looks like Western Digitals are a little bit better. 1.1% for a Western Digital, 2.86%. It's hard to say. The Seagates, these Seagates, 1%. I mean, this means 1%. So if you have, there's a 1% chance the drive's going to fail in a year. If you do look at, you see the HGSTs, those are generally more reliable. They're often maybe a little bit more expensive, but they're a little bit more reliable. So this Q1 thing, I used to think Seagates were better. Now it looks like Western and Seagate are kind of the same. This one here may just be an outlier. Now let me navigate around Newegg a little bit. I jumped over to laptop internal hard drives. Again, they kind of look the same. Frankly, they're priced pretty much the same. Capacities are going to be a little bit lower. You notice before for the desktops I was seeing 4 terabytes. Now I do have some, but the more popular size in desktops are probably 1 terabyte, whereas in mobile is 1 terabyte. Again, same lines. The components are often the same. The platters are the same. The heads are the same. And if you are doing some repair, you have to understand what drive is currently in your system and then look for a matching drive. Just a couple other notes. Western Digital has, again, their own color scheme. Blue is kind of their general purpose drive. Black is a performance model. Let's just pick on Western Digital and take that size. I don't know that I'd ever buy a refurbished drive. So blue is kind of their low end. Oh, here they have a hybrid drive. This has 8 gigabytes of SSD memory coupled with a 1 terabyte magnetic drive. If you don't have a lot of empty connectors, maybe you're mobile, you don't have a slot for an SSD, this can give you some performance benefits. I used to have a PC with an SSD, with a hybrid drive, SSD combined with the magnetic hard drive. Then you go up, then you start seeing other color Velociraptor, black drive. So each manufacturer has their own kind of high-end to low-end scheme. All right, let's go back up to hard drives. Actually, let's go to components. And we're going to come down and we're going to look at SSDs. Let's see. And again, internal and external and enterprise SSDs, if you're working in a data center, they might just be using off-the-shelf consumer-grade internal SSDs, or they might be using enterprise SSDs, which are, again, usually come with a little bit more warranty, perhaps a little bit more reliability from the manufacturer. Maybe the manufacturer tests them more, uses a higher quality of part, perhaps, or just simply charges more. And let's actually look at this before I do that. Kind of, you can see here's some form factors. The 2.5 form factor, there's that M2. There are a few hard drives that plug in PCI Express slot. A slightly older standard called mSATA, which is really just replaces the cable. This is a direct SATA connector on the motherboard, so you don't need a cable. This is a different kind of connector. So let's, just as a comparison, let's look at internal. So if we remember, we were seeing 1 terabyte or 4 terabyte drives for as low as $115, maybe up to $150. I don't think I can actually see a 4 terabyte SSD. They don't seem to list them. So I'll just do something that's, say, half that, or 1/4 that. Let's see. And I'll just take, well, it doesn't make a difference, the form factor. You notice that the manufacturers are different. Magnetic hard drives were Western Digital and Seagate were the big ones, and then Toshiba sells some. Here, Samsung, Crucial, Intel sells a few. Really from Newegg anyway, it's really Samsung. There are these other manufacturers, but they might be using Samsung chips, or possibly Crucial chips. So Crucial and Samsung. Crucial is a trademark name of Micron, which is that company in Boeing, or at Boise, not Boeing, Boise. So let's just look at a Samsung. Gee, they're really overloaded with Samsungs these days. There are other good brands. SanDisk is another big brand. I think I have a SanDisk and Transcend, but in this size, Samsung seems to be the key player. So anyway, I'm just kind of looking at a 1 terabyte drive, trying to get an idea of average price. So 1 terabyte, around $300, $350, up to $400. So you're paying, 3 to 4 times as much for a drive that has 1/4 the capacity of the magnetic hard drive. So magnetic hard drives still have a place in the world because they're cheaper. So let's go back to the slide set and talk about how you would use an SSD drive. So I've got 3 usage models here. Here we have the CPU, 16 gigabytes of RAM, an SSD that sits between the RAM and the hard drive, magnetic hard drive. 64 gigabytes is not enough to store an operating system and all the typical files that you might need, so it's working as a cache. So the CPU is going to look in RAM, then it's going to look in SSD. Finally, if it doesn't find it in those places, it's going to go look at the hard drive. Total max storage is really just 2 terabytes. We don't really count 2 terabytes plus 16 gigabytes. Everything is controlled by this maximum capacity here. The SSD is just a copy of selected items from the hard drive. To the computer, you're just going to see, or to the operating system, you're just going to see a single C drive. You don't need to worry about whether your files are here, or in RAM. The computer just takes care of that for you. Here's another model where we don't have a hard drive. This is more expensive. The 2 terabyte drive might be $80, and this might be smaller SSD might be $100, $90 or something. Here we're probably paying $200 or something for this, maybe $150. This is more expensive. We don't have the magnetic hard drive. It's faster overall. Nothing ever goes to the slower magnetic hard drive. It's all coming out of the SSD. On the other hand, we have limited space. So this is probably not the model if you're storing lots of movies. If you're storing lots of movies, maybe you use this plus an external hard drive. In this model here, you separate into 2 different directories, and you have 2 different letter drives. So again, the CPU is always looking for RAM, but then depending on where your files and data are, it's either going to go for the hard drive or the SSD. And here your total storage is 2.5 terabytes. So you're not losing anything because it's being cached. There's a balance of storage versus cost. It's a little bit more complicated to maintain 2 drives because you never quite know where your file is. So I have this kind of set up on one system. My operating system and frequently used programs are here. I keep documents and other things over on the magnetic hard drive. Let's see, SSD. A little bit more on drive form factors. Hard drives come with that cache I talked about when I was looking at Newegg. Cache tends to come in 8, 16, 32, 64, or up to 256. Also talked about that hybrid drive where you've got an 8 to 16, maybe a 32 gigabyte SSD in. The hybrid drives you don't see so much anymore. They were out there for a while, but now with the prices on SSD, even though they're expensive, they are coming down. People just go straight to an SSD. Recently, last year, Intel introduced something called Optane. It's a new technology just out, and it's not system memory, nor is it a true SSD or hard drive. It's something in between, and I don't know how well it's doing, but it's local, and so it's a 3-dimensional type memory internally. You, the user, really don't care, but it's some kind of new memory technology. And here's a interesting graph that shows the comparative speeds. So main memory is really fast. And this is all relative speed. So main memory latency is 1x. Size of data means 1x. This has to do with cost, really, or space. Anyway, that's SRAM. In this space, you can store 1 unit of data, and it takes 1 unit of time to access. This is SRAM. This is in the CPU. Then we have system memory here. This is DRAM. It's a little bit slower. It's 10 times slower than the cache memory on the CPU. But on the positive side, whether you're counting it in size or money, it can store 100 times as much data. Okay, then before we jumped up to the SSD, which is quite a bit slower, 100,000 times slower than the cache memory, but it can store 1,000 times as much for the given space. Then up here we have the magnetic hard drive, which is 10 million times slower than SRAM, or 1 million times slower than system memory, but it's very efficient at storing things. So this Optane is something in the middle. It's 100 times as slow, but stores 1,000 times the data. And Intel's been making these, and they sell them in a 16 gigabyte or 32 gigabyte size. And it's really just functions in the cache model. CPU is going to look here, then it's going to look here, then it's going to look here. But 32 gigabytes, that certainly lets you store quite a bit of stuff. Whether it takes off or not, it's kind of, do you spend your money on an Optane, or do you just simply add more system memory? Oftentimes your best choice is to add system memory, but we'll see how this goes. Now, we have different ways to connect drives and storage. There's a term that's been with us since the 80s, the AT attachment interface. And this was a AT attachment, AT API, ATA, a system for connecting peripheral drives to PC. For many, many years, PATA, which is Parallel ATA, it was a short, flat, wide ribbon cable, which kind of got in the way. It was hard to connect. It had a limited max speed. Because of the cabling and how it fit on the motherboard, usually you only had room for 2 or 4 hard drives or optical drives. You had to share a cable, 2 devices on one cable. You couldn't unplug a drive. Certainly worked for the time, but about 10 to 15 years ago, even though optical drives still connected with PATA, they moved to something called SATA, Serial ATA. And that is the most common in the case connection for drives that we have. It's a much thinner cable. Actually, the power cable is bigger than the data cable. It is a point-to-point connection between the controller or the host bus adapter and the drive itself. The narrow cables were longer, better airflow. One of the big things was that they were hot swappable, and there was no drive limit, meaning as long as your controller had connections, and some controllers have quite a few. Some motherboards can support 8, 10 SATA drives. There was no drive limit. The big thing is, though, it was hot swappable, and what that means is that while the system is on, you can unplug a drive and plug a new one in. So here I just found a picture of some kind of server with a data center. These are all probably magnetic hard drives here. So this is meant to store a lot of data. In a data center, you have racks and racks of these, and like we looked at with those drive statistics, these do go. If you have enough, there's one going bad every day or every hour. And so as part of a technician's job in a data center, there'll be some software indication, a light somewhere, a page. The system will detect that, say, this drive failed. Now there's some various redundancy techniques that we can use so we don't lose the data, but the drive fails. And what the technician's job is to go to that unit, push this button, this pops out, and they pop a new blank drive in, and then the system takes care of reloading the data in. But the nice thing is the system does not have to be shut down. These can still be going full speed, servicing customers, taking care of business, and you can hot swap a drive while the system on. That was one of the big benefits of SATA, hot swapping. Let's skip that. That used to be important, AHCI. These days motherboards all work in the same AHCI mode. Be rare that you would find an older system might have an IDE mode, and you had to keep track of, is the motherboard drive controller supporting IDE mode? Is it doing AHCI, or is it doing a RAID interface? Now SATA comes in different flavors. In Newegg, usually it says SATA 6 gigabytes. Sometimes it says SATA 3. SATA 3 is equal to SATA 6 gigabytes. This is a raw speed, meaning that over that SATA link it can handle 6, not bytes, but gigabits per second. Now there's some, overhead encoding, so you don't really quite get 6 gigabits per second, but it's still fast. Now there's an older style of drive, let me move it up a little bit, called SCSI or SCSI, Small Computer System Interface. Long before SATA came around, enterprises and businesses and industrial applications would use a SCSI based interface, and that allowed you to chain drives. It allowed you to have more drives on a system. Chaining drives means you can combine drives. You just chain the cable. One cable went to another. It's been around since the 70s. Here's a drive where, I guess that's a SCSI, it says zip, where you would just simply stack these up and you would just chain the cables together. It used to be the choice for redundant array of individual disks. I think you only see this in really old legacy systems. You can still buy SCSI drives. They're kind of expensive, and you don't have a lot of choice, but they're still out there. And this is kind of a general chart to give you an idea of the speeds in drives. And eSATA was for a while it existed out there. It was an external SATA connection. All the SATA connections we've looked at so far are meant to stay inside the case. This was you had an eSATA connector on the back of your laptop or on the side of your laptop or back of your case. But we get an idea of SATA speeds. This was more of an enterprise data center connection. I don't know how common it is anymore. IEEE 1394 was a high-speed interface that's pretty much been supplanted by USB 2.0 and USB 3.0. You can see that USB 3.0, in terms of its raw bandwidth, in terms of bits per second, is almost as fast as SATA, functionally the same. You also kind of see why if you're connecting up an external hard drive, if you have a choice, you definitely want to go for a USB 3.0 speed, not a USB 2.0 speed. You can see the big difference in speed. External hard drives over USB 2.0 are quite a bit slower than internal hard drives. SCSI is still pretty fast, but again, not very common. Something called Thunderbolt, a new standard, or it's not totally new. It's not really. It was supposed to take over for SATA and USB. I think practically speaking, USB 3.0, and I don't have it on here, but there's USB 3.1, sort of are starting to replace the need for Thunderbolt. Now, this is a common, important topic for businesses and enterprises, is protecting your data. Now, if you have a PC, some of you may have had a drive failure. It's not great. You lose pictures, you lose files, you move on with life. But if you're a business, you can't afford to lose data. So in a business, they want a way to protect their data that's stored on magnetic hard drives or SSD drives too. But because the rule with hard drives, it's not if they fail, it is when they fail. And so there are different ways to organize your data to minimize the impact of a drive failure. And that is called the Redundant Array of Inexpensive Disks, or RAID. Now, RAID comes in different levels. RAID level 0 is really what we call disk striping. If you have one, by the way, if you have one drive on RAID 0, it's just all your data gets stored on one drive. It's nothing, just like normal. There is a way, though, on some systems to, if you need more capacity, you can stack the drives on the drive controller, and the data is striped. So segment 1 goes here, segment 2 goes here, segment 3 goes here, segment 4 goes there. If there's some parallelism here, it means that you also get faster transfer rates, meaning all these 4 segments get transferred at the same time. The bad deal about this one as far as redundancy, though, is there is none, because if one drive fails, you've lost a fraction of your data and you really can't reconstruct that. It's RAID level 0. There is used to be a RAID 2 and 4, but they don't get used anymore. Next one that is probably used is RAID level 5. So that is disk striping with distributed parity. So these are all A, B, and C are files. A1 is a part of the file, A2 is the second part, third part, and so on. AP, that is the parity. So they analyze these 3 parts of the files and come up with a parity bit, really. And what that does is, if, for instance, we lost disk 2, the computer can take A1 and A2, take the parity bit, and reconstruct the data on the fly for whatever was on A3. The parity bits are often also distributed among the drives, so that you don't really have one drive that just stores parity bits. And if you were to lose, by the way, if you were to lose disk 3, you know, at least as far as file A goes, you'd still have A1, A2, you'd still have full of A. And so this is where that hot swapping comes in. So if you have a drive failure, if 2 fails, the system for a while slows down a little bit while it reconstructs the data on the fly. You come along, you put a new drive in, it will refill this disk, and then it will go back to normal speed. This does require at least 3 drives, 2 for data and 1 for parity. This one uses 4 drives. There's RAID 6, which actually has really 2 basic parity drives. It takes more drives. What this system allows you to do, though, is you can have 2 drives fail at the same time, which is statistically not likely, but still possible. You can have 2 drives fail and still, you know, maintain consistency. Maybe this would be more appropriate for some place where you actually can't get access to it right away to swap out the drive. There's also some other proprietary RAID implementations. Typical RAID implementation in terms of your personal or home office computer. Most motherboards support RAID. They've got all the SATA connectors, and you can switch and configure RAID on. A lot of people, if they do it, will, for instance, buy 3 1TB drives and then get 2 terabytes of effective storage instead of buying 2 terabytes. It costs you a little bit more, but you get redundancy, and you're totally protected against a single drive failure. In a business, it's more likely that you'll have PCs with individual drives, and those PCs will be backed up daily to a network-attached storage device or RAID enclosure. These are things that sit on your network. These are the drives in there. They take anywhere from 2 to, well, there's some that take 2, some take more. If you lose a computer, either for whatever reason, lose the drive, you know, the IT department or you will, you know, restore from this system. So here's a practical example of a network attached storage drive. So Synology, and we can look at their products in a minute. That's a company that makes network attached storage drives. They have a little calculator here. So if we want to configure our drive, let's say we're using those say $120 4TB drives, and you can see here that if I do, they have their own proprietary thing called SHR. Basically 4 terabytes are used for data, and the other 4 terabytes are for mirroring. And in mirroring, just to review real quick, I skipped over a little bit. Mirroring was the technique of having 2 drives. One stores data, one is a backup. If the main drive fails, the backup just kicks in. So everything that's written to this drive also gets written to this drive. But in practice, when it's running, only this drive is reading from until it fails. So that's RAID level 1, that's mirroring. So so here I can support two drives, gives me 4 terabytes of storage. Now if I add a 3rd drive, that opens up some other RAID possibilities. I can do RAID 5. Here 2 drives are being used for storage. This is for the parity. I can put more in. If I put 4 drives in, I also have some other choices here. You do RAID 10, which is, you know, takes into or protects me against multiple drive failures. They do support a RAID 6. There was mirroring, which is kind of a waste with this many drives. Mirroring only works when you have 2 drives. And just kind of looking at their low-end product is this. Let's see. Let's find a picture of it. Oh, that's the software. Value series. This is a network attached storage device. These are good for mirroring. This one will support the RAID with parity. These actually are little computers. They come with memory, has a dual core, but smartphone class, Raspberry class processor in here to connect to your network and also handle your backup needs. Now, how you connect a drive. So, depending on which drive you have. So, PATA. PATA involves setting master and slave bits. There's jumpers. You have to select the right cable, whether it's reversed. If you have to do that, you better do some research. Look at your book. SATA, on the other hand, it's very trouble-free. Cable only goes in one way. On some systems, you may want to, on your motherboard, plug in your first drive as SATA 0, but it really doesn't make any difference. SSDs, there's that M2 connector. See how it fits flush with the motherboard. Oops. Is that M2? I think that's M2, not mSATA. It's faster. SSD configuration. There's a word you'll sometimes see around called Smart Response. That lets you configure the SSD as a cache. Intel used to ship software with all the systems that ran their processor that supported Smart Response. SSD, this is again kind of a review against that slide I did before. If you do have this model, though, the thing you have to remember is your OS goes onto the SSD and your files go onto the magnetic hard drive. Now, partitioning. So that hard drive, whether it's an SSD or magnetic hard drive, is unformatted. It's just a bunch of bits or little magnetic fluxes. And so there's a lot of stuff that goes into partitioning them or subdividing them into lettered drives that Windows can assign a letter name. So hard drive must have at least one partition. It is possible to put multiple partitions on a hard drive. It's unusual to see that anymore, though. Now, one important thing about a hard drive is that on a drive that's used to boot the system, there's something called a master boot record, and that is a small amount of code that takes care of the booting up from process. So the BIOS handles the power on self-test, gets you up to that menu where you can make selections. The next level would be that you want to actually start booting the operating system, and that starts from some code stored in the master boot record. And that is always a fixed partition or a fixed location in the partition table. It's always the same for all drives so that the computer knows where to look. If it's booting Windows, it's going to have some Windows code here. If it's booting Linux, it's going to have some Linux startup code. There's only one MBR per disk, and if you have multiple disks in a system, really only one drive is the boot disk. On other drives in the system, that MBR will be there, but the computer's not going to look for it because it's not the first drive to boot from. And the master boot record and partition table. The partition table tells the computer or the operating system how all these tracks are organized, and that's going to be stored in the boot sector. Oops. Now I'm going to go fast through this because generally these days we don't have multiple partitions on a drive. Used to be more complicated. Used to have to pay a lot of attention to this. Now it's one drive letter per hard drive usually. And I only say this part about dynamic disks. The book spends a little bit of time on it, but dynamic disks was really just a software way to deal with hard drives, to deal with RAID. These days, RAID is usually hardware-based. It's on the drive controller. It's not an operating system function. It's rare that you will see a dynamic disk. If you ever encounter a PC that has a dynamic disk in it, then you should be worried, or not worried, but it just takes a little bit more thinking about how to deal with it. Sometimes partitions on hard drives are not visible. There's no letter drive, and that can be used to store backup copy of the OS, backup information. On Linux, there's a swap partition. That's to store data that's a little bit too big to fit in the memory. On Linux, you don't really have a letter drive. You have a name drive. There's an invisible partition that you can't see that works as a page file, like the Windows page file. Oops. Now there are partitioning tools. Windows comes with something called disk management. There's gparted, partition magic. They give you these tools that tell you what, how much capacity is on the drive, what partitions are there. This one has it's actually kind of a small drive, but a little bit of Linux swap located. It's a 10 gigabyte drive. Must be an old picture. Has 2 partitions. And here I brought up a tool in Windows called Disk Management. If you just type Disk Management in the search bar, it'll come up with this. I don't have too many systems on this system, or too many drives on this system, but I've got my disk 0. Again, some reserve stuff to store some operating stuff. This is my SSD. I have a 256K SSD. It's my boot drive. Contains my primary partition. I have some recovery space, and somehow during partitioning I ended up with a little bit of half a gig that never got allocated, and it's not worth it to resize this partition to pick it up. This is my main system drive. It's a 1 terabyte drive. Again, there's that little bit of system reserved I can't ever seem to get rid of, and I don't really care about. I have a let's see, this is plugged in to the SATA port. This is actually I have a dual boot system. This is actually a Linux. This part is Linux, and this part is Linux swap. I can restart my system and have it come up as Linux. And so that's why this doesn't say anything about, there's no letter drive, it just says primary partition, doesn't say boot. This actually contains my Linux operating system. And then I have a little bit of space on the end that's used for a couple backup things. And then I have this. This is actually connected with a USB 3.0 connection. It doesn't say it. I don't know if I can actually see the fact that it's on a USB 3. Again, a 1 terabyte drive is just used to store data. So once the disks are formatted or partitioned into tracks and so forth, there's also a need to organize it into a file system. And so each operating system has a certain type of file system it likes. And the file system, FAT32, NTFS. So FAT really stands for File Allocation Table. And it's really just a big table that connects the description or file name with its actual physical location on the drive, whether it's an SSD or magnetic hard drive. If it's magnetic, it's which track, which sector that file is at. Different kind of, there's FAT16, FAT32. This just has to do with the number of bits used to represent the file table. FAT32 can address or handle a larger disk drive. NTFS stands for, it was an old term, Windows NT file system. It's a newer, more sophisticated file system. USB sticks are often FAT disks. You never see it, but on a Windows system it's NTFS. On Linux has a different way of organizing its files, and that means you can't take a hard drive or any kind of drive formatted for Linux, plug it into a Windows PC, and expect to read it. On the other hand, Linux systems will be able to read an NTFS system, but it doesn't go the other way. And Linux file systems are often stored, or they use, lately it's ext3 and ext4, just the name of the file system. So in general, all these file systems use something called a file allocation table, and it just keeps track of the sectors that store various parts of the file. FAT16 has fewer sectors. FAT32 uses 8 digits, so it can store more sectors or keep track of more sectors. Often on drives you can have bad sectors where the magnetic flux is damaged, or it's not storing the value. On an SSD you might have elements that just aren't working anymore. So the file allocation table keeps track of those bad sectors or bad areas and marks them with a special code. And here's kind of this is a magnetic hard drive, but it's an example of fat storage. On that track are clusters, and a cluster is actually quite a large area, frankly, but several bits. Clusters have a physical address, and then here's their status. And so this is an empty disk with one bad sector. We come down to here, and there's a file called mom.txt, and in the file allocation table, we indicate that sector is busy, filled with mom.txt. Mom.txt gets a little bigger. It takes up two clusters, and then FFF, that's the indicating that it's the end of the cluster. So files can actually be stored here, and then it skips over the bad sector and then puts the end of the file here. Now there's something called fragmentation, and it's when files are spread across clusters. They're not all continuously in that circle, and that can slow the system down, because if you have to read this cluster, skip over one, or even worse, if files are stored on different tracks, it requires the heads to move back and forth and the disk to spin. That can slow the system down. Windows 7 and above automatically defrag, but it's just interesting how things cannot be stored efficiently, and the defragmentation process that happens automatically moves clusters around to where the file is just like in a continuous ring. And fragmentation occurs, by the way, when you start deleting a lot of files and creating a lot of empty spaces. The system will keep trying to just fill in the next available space, whether it's efficient or not. And here's a picture of the disk defragmenter. You can still run it, but usually the disk is pretty well defragmented. But what it means is that the blue is contiguous files, red is files that are split, and then some things need to be in the same place every time. That's the green. If you were to run this and it was badly defragmented, you would see these colors jumping around until most of it becomes blue. I think at this point I captured it. It was 1%. Now, disks, optical disks, USB drives, hard drives, those are what we can make those into bootable disks. So a CD-ROM, DVD-ROM, Blu-ray, USB drive, by itself it's not bootable. It doesn't have that special code in it that at the boot sector, the boot record to boot up. So you have to use some tools to actually create a bootable drive. And when you put that's why I don't think anybody had this problem, but on the Raspberries, if you just copied the files over to the SD card, it wouldn't boot your Raspberry. You had to use a special program to download an image of the operating system, which put the boot information in the right place. Let's see, I actually already jumped ahead and I showed you the disk management tool. It shows you which disks are present. And as a tip, by the way, if you have stuff plugged into a system and you don't see it, your first go-to thing should be to launch the disk management tool, and it will show you the disks that are plugged in, but perhaps Windows has not allocated them a drive letter for whatever reason. So like on this view, there's disk 0 plugged in. So second disk plugged in, but Windows cannot see it because it's not been, probably here, it's not been formatted, and the file system has not been installed, so it just says unallocated. I can see it here, but if I was on Windows File Manager, File Explorer, I wouldn't see it. Now let's skip over some stuff. Now I'm going to skip over this stuff on dynamic disks. I know it's still in slides, it's a little bit in the book, but I don't ask any questions on dynamic disks anymore. Now, disks again can go bad, and there is a program called checkdisk you can run, chkdsk, from the command prompt, and there's also a way to run it through the command or computer management system. I tend to just type checkdisk. it will look for lost clusters or chains. If a file gets corrupted, you might have part of the file still on the drive. The file allocation table lost the name of the file, but it still sees that there's data in there. Sometimes this will resurrect a bad drive. Windows, luckily these days, actually kind of takes care of most of this. If Windows finds a problem, it will fix it automatically. If you bring up the disk properties, you can also find the right option to say click it for error checking and it will handle it on the next reboot. There's also a program on Windows called Disk Cleanup. And if you have a smaller disk and you need some, it's filling up, you can do disk cleanup and check the boxes of things you want to delete. It'll go through, it'll delete temporary internet files. Sometimes if you've had multiple operating system patches, that takes up a lot of space. This will get rid of those. Now let's look at troubleshooting for disks. So kind of problems you might have are installation errors, data corruption, and dying hard drives. Now installation, basically plug a disk in and it doesn't show up on the Windows file manager. Could be a number of things. Could be a problem with the hard drive. It's possible the controller failure is bad, or the controller's bad. Things to check: make sure you've connected your cables. Make sure that in the BIOS, some older BIOSes require you to actually enable drives manually if you put them in. Sometimes you get these kind of errors if it's a CMOS problem. No boot device available often means, again, maybe you didn't set something up in BIOS, maybe the battery went dead, maybe there's no OS, maybe the drive is bad or not formatted the way you think. You can have partition problems, and this is something that gets solved by running one of the partition tools to see what's actually there. That'll help you out. Now, data corruption. That's probably more likely the kind of thing that's going to happen. And it could be caused by many things. Power surge, accidental shutdown when something is trying to write to the disk and the power shuts off right in the middle. Viruses can cause that. Things will show up as, files will be missing or corrupt, unable to load file, cannot find command.com. Windows these days, luckily, will take care of most of that. If you do get something like this and Windows is not handling it, best thing is to basically Google the kind of error message and see what you get. See what kind of help you can get. Now, a dying hard drive. If your magnetic hard drive is making a lot of noise, that's not good. If the drive fails all of a sudden and it's your boot system, it'll say no boot device present, or it just won't see it at all. So here I've loaded a utility that I have on my system called Disk Checkup, and it shows me the 4 disks I have installed: a couple Samsungs, a Western Digital, and a Seagate. That's my SD drive, or SSD. Let's see, this is now on all drives have this something called Smart, and if I click on that, this particular, let's see, which one is okay? This one. So this drive, which I know happens to be my H drive, the disk is keeping track of various parameters. And this software kind of looks at the parameters, and now it's predicting that my drive is going to fail as soon as August 2029. I've seen this date change. This is an older drive. It's starting to get some errors. This one's a newer drive, and if you were to compare, it has fewer errors. Seek error rate, so that's actually at times been pretty high. On this one, the seek error rate is 0. So this kind of tells me I can't really trust that date, but this tells me based on information, this drive's going to fail. whether it's 6 months from now or a year from now or 2 years from now, it's going to fail. And that's the drive itself telling me that. Hopefully you spot it before then. I should be replacing it soon. But when it does these kind of noises, that means that it's not finding a track. The heads are going crazy. All right, now let's continue on to optical drives. So optical media, we call it optical because a laser is used to extract the ones and zeros, so light, optical light. Could be a CD, DVD, or Blu-ray, just generically called optical drives. How a CD and a DVD work is that data are stored in microscopic pits have different reflectivity. So a 0 reflects slightly differently than a 1, for instance. It's burned in with a power laser on a glass master. The data on a disk is actually on the top, just under the reflective label. It's not on the surface on the bottom, it's actually on the top. So scratches on the shiny part actually are not bad. A scratch on the label part will cut through to the reflective surface where those ones and zeros are and cause it to not read. Just CD-ROMs and DVD-ROMs have different speeds at which they can be read and written. These days we're pretty much at the faster speed, so we don't really pay much attention to that. CD, DVD, Blu-rays also have normally from a distribution point of view they're read-only, but you can buy rewritable drives. Now these days with the increased size of magnetic drives, SSDs, flash cards, and external drives, few people store their data on writable drives anymore, but you can do it, and it works by using a laser to heat a pocket of dye that's inside each little 1 and 0 pocket, and then use a laser at a different frequency to clear it, for instance. Okay, I'm going to kind of skip through this. Things that are probably important to know. Let's see, let me find this thing here. Let's see. What? So CDs, I glossed over. CDs usually have a capacity of about 700 megabytes. DVDs come in a single side, single layer. You get about 4.37 gigabytes. This is a dual layer, so a laser uses slightly focused differently to get a different layer inside the drive, or inside not the drive, but inside the disk. Those will store close to 8. And then dual-sided dual layer, you get up to 16. And Blu-rays, on the other hand, will store 25 gigabytes on a single layer and 50 gigabytes for a dual layer. Discs, these kind of discs are probably used mostly for archival storage and some distribution these days. Optical drives, they kind of all look the same. They're all standardized, all fit the same. Most of them these days are all SATA, so they just plug in the same as a hard drive. One thing to remember about, there's a term called ISO files. And an ISO image is a complete copy of the media of an optical drive. And so if you want to create a distribution drive or something that's bootable, you don't want the files, you want the entire disk image, which is a track to track, bit to bit copy of a disk or drive. And that should do it.